prazer de poder dar uma aula aqui no Brasil. Cada vez que eu posso ir viajar para o Brasil, eu agradeço muito, porque eu gosto desse país. E até vou dar a palestra em português. Não sei se vou conseguir falar a história completa em português, porque isso foi a minha primeira viagem para o Brasil. Estamos falando de 1944, aqui, a 49, atravessando o Equador e chegando em Rio de Janeiro, que tinha uma aparência bem diferente em 49 do que tem agora. Alguns anos depois, ou seja, na época onde o Jânio Quadros era o governador do estado de São Paulo, ele está falando com meu pai aqui, que está tentando de vender aviões holandeses para o Brasil. Hoje em dia o mundo mudou, são os aviões brasileiros que são vendidos para a Holanda e Inglaterra. Tá, mas então o problema então é que eu não tenho o hábito de falar dos assuntos científicos em português. De vez em quando vou ter que usar os termos em inglês. Vamos começar com o fundamental da informação na óptica e também na óptica eletrônica e os partículas com que a gente forma as imagens. Isso é uma história muito velha. O Isaac Newton sempre falou que a luz são bolinhas, como se fossem pedrinhas que transportam a informação. E, no mesmo tempo, o Christian Huygens, um pouquinho antes do Knight, falou que a informação das imagens é transferida por ondas. Então, isso foi uma briga entre esses dois pesquisadores de 300 anos atrás, 400 agora quase. E, no fim da história, então, aqui a briga entre o Isaac Newton falando que luz são pedrinhas e Christian Huygens que falou que luz como em ondas. No fim do século XIX, todo mundo sabia que luz era ondas e não dava para explicar tudo que tem que explicar com a luz sendo corpuscular. Só que no começo do século XX veio Albert Einstein e falou que as duas coisas são aceitáveis, tem coisas que tem que explicar como como particles e coisas que tem que explicar como ondas. Mas, então, no fim do século XIX, vamos voltar um pouquinho antes do Einstein, o mundo da pesquisa sabia que a luz foram só ondas. Mas elétron é uma outra história. Isso também é uma publicação do fim do século XIX, e esse aparelho foi construído nessa época para mostrar a natureza dos elétrons. Agora eu tenho que mudar para inglês, desculpa, porque eu não conheço os nomes desses aparelhos em português. Mas so this is a vacuum tube. In the cathode here, you're emitting electrons, and the electrons leave the cathode in the direction perpendicular to the curved surface of the cathode. And if you have this curved cathode and nothing else, then you will see the electrons being focused on this little screen here. You would see the electrons travel through vacuum because the vacuum was not very good with the pumps of the end of the 19th century. So you could actually see the electrons or the rest gas inside the tube light up, and you would see the electrons hit that little screen. But if you put a magnet on top, then these electrons get bent by the magnetic field, and then they no longer hit that screen, but they start hitting this little wheel, and the wheel starts turning. So this is a fantastic practical proof of electron being particles. At the end of the 19th century, light consists of waves. Electrons are particles. That was the status of the science 110 years ago. However, then at the beginning of the last century, we had, this beautiful illustration comes from this book here. It's called William Bragg, The Universe of Light. And it's a book that I found in my father's library as a kid, as a teenager. And it had fantastic pictures in it on optics. And little did I know who Sir William Bragg was as a 14-year-old. But I love the pictures, and later, when I became a professor and was teaching and got hold of this book again, I was looking at the pictures, and many of the illustrations in these pictures in this book I now use for teaching. So this is only one of them. There will be more coming. So little did I know that he had such a good fundamental understanding of what happens in diffraction and when you're imaging an object, that he is very good in explaining these things. And then came in the beginning of the 20th century came Louie Debroy, and Louie Debroy got the Nobel Prize in 1929, and he got it for his discovery of the wave nature of electrons. So 30 years earlier, there was no discussion about electrons being particles, but then here he suddenly, Monsieur Louie Debroy, when quite young, you threw yourself into the controversy raging around the most profound problems in physics. You had the boldness to assert, without the support of any known fact, that matter not only had a corpuscular nature, but also a wave nature. Experiment came later and established the correctness of your views. And this standard formula today is what you use to calculate the wavelengths of electrons. And here, for 300 kilovolt electrons, the wave of the electrons is 0.02 angstrom. And because the wave of the electrons is the wavelengths of the electron is so short, you can look at very small things with it. So this was Louie Debroy. This realization that electrons also had a wave nature made that a whole field of science that was developed for waves was suddenly applicable to electrons. So very simple things like a single point vibrating in space and creating concentric waves, or you can have an extended source vibrating in space and creating waves, and you then start to recognize a wave pattern around this that has a strong directionality in these two directions, the horizontal direction. So with the whole appreciation that electrons were wave, the whole field of optics, or Fourier optics, really became open for electron microscopy as well. And here we see a Fourier transform for beginners. So this is the first diffraction experiment where a child sits there and focuses the light from the sun. It's a parallel beam hitting this lens here and focusing it into a single point. Now, that's a very fundamental operation. It's actually a diffraction experiment. Here's the diffraction experiment explained. So you have the sun very far to the left here. It's because it's so far away, you have plain parallel waves hitting this lens. Forget about this piece of glass here in the front focal plane for now. And then it focuses into a single point in the back focal plane. And so all the energy goes to one single spot, and you start burning the leaf if you focus on it. But the thing to remember here is you have a constant hitting this lens and then being transferred, then transformed by this system into a single, very strong diffraction spot. Now, let us do something to this. Is just a piece of glass, but now you take a stone and you scratch it in the middle. That little scratch will start, becomes a center of secondary waves itself. So you have the plane waves hitting this object, and then this little spot will start. It becomes a secondary radiating point, and from this point, concentric waves emerge, and they hit the lens. Since this point is in the front focal plane of this simple lens, after you pass the lens, you have parallel waves coming out. So we saw in the previous slide here that a constant was transformed into a single point. And here you see a single point being transferred into a constant. So this optical system here is capable of doing these fundamental operations. We'll get back to that later. This is the Fourier transform that you've already heard of a lot these days. Now, let us take that object here, and instead of having a single dot there, we put a collection of dots in the front focal plane of that lens. And now comes something that you all know, that if you have a regular array of point scatterers, these are secondary scatterers, excited by this incoming plane wave, then from each of these points you have these concentric waves being diffracted, and these concentric waves from this spot and from that spot and from that spot start interfering with each other. And it is relatively simple to see that this wave front here that was emitted from this point scattering one period ago is in sync with the wave that's being emitted from the next one here now, and is in sync with the wave that had been emitted from this point 2 periods ago. So in specific directions, everything is in sync, and the waves, the secondary waves, start to reinforce each other, and they form by constructive interference, you get a strong diffraction peak going out in that direction. And if you have one going out in that direction, then you automatically also have one going in the opposite direction. This is the +1 diffraction peak, and this is the -1 diffraction peak. The zero order beam is still going ahead, so you still have this very strong parallel beam just transversing the whole object and continuing its travel without having been diffracted at all. So one object that is periodic will lead to a sequence of diffraction directions here. So you see that here modeled in a simple grating of a periodic array, and you see that in specific directions you have this reinforcement of the secondary waves coming out of this object. If you then go back to the Universe of Light by Sir William Bragg, you see these beautiful pictures where I did this here many years ago by painting this, but then you find exactly the same illustration in Sir William Bragg's book of 1933, and imagine him sitting there drawing all these circles by hand to find out that in certain directions you have these reinforcements, and in other directions they cancel out. Here, this drawing that he made, or his technician, I don't know, if you have an arbitrary directions, these waves that contribute to it are all out of phase and nothing happens. But in specific directions, they all coherently add up, constructively interfere, and you have a strong diffraction peak from this periodic object. The periodic object can have all kinds of different properties. And the two most familiar ones are the amplitude object and the phase object. The amplitude object is like a slide. Nobody knows what a slide is anymore, but a photographic picture essentially where you have dark areas and light areas, and you put this in the slide projector, then less light will go through here because there's more absorbing material, and more light will go through here because there's less of that. So you have light energy being taken out of the parallel primary beam. That's one type of object. For electron microscopy, the most important type of object, normally, certainly in biology, is the phase object. And the phase object, you have a periodic signal like here, but in essence, all that happens if you have a plane wave hitting this object is that you will have a wave coming out here, and here it will be delayed a bit compared to here because there's less material to travel through. So you get a wavefront coming out at the back of this object. And in reality, you can have all kinds of combinations between phase object and amplitude objects like this. What interests us most is the phase object like here. Now, here is just the same simple lens system that I showed you before. The girl sitting, or the boy sitting there with a magnifying glass. And instead of a periodic array of dots here, we now have an object, a sine wave as object. And if you have that's a pure sine wave as an object, you will get two diffraction spots from that, one at the +1 direction and one at the -1 direction. What I didn't tell you here is if you have an array of dots like this here, then you not only get the +1 direction, diffraction direction, but you may also have the +2 direction, because the wave that's being emitted here, was emitted here 2 periods ago, is also in sync with the one that's being emitted there. So you can have a whole array of diffraction peaks, as you all know. But if you have a pure sine wave as a phase object or as an amplitude object, you have in the back focal plane these two strong dots at the +1 and the -1 diffraction direction. And of course, you always have also the zero order diffraction beam coming out, continuing still. This here is again that same story, but done as a little model calculation by Ardan Patwardhan. Here's the periodic object, and the waves coming out of here, parallel waves, but with certain direction preferences now, as you can see. And here it hits the lens, then focuses these parallel beams that go in specific directions in the +1 and the -1 diffraction direction. This is on a micro scale, because you can see there's only a few wavelengths everywhere. So it's just looking at things at the absurd, on an absurd scale almost. You can do that in the computer easily. You cannot build this. So this is the zero order beam, the +1 and the -1 diffraction pattern. This is also very important for understanding optical systems. And this is here the Rayleigh resolution criterion. If you have an object with a periodicity of D here, then the diffraction spot that corresponds to that will go off in a certain direction here. And the diffraction spot, the smaller D, the higher the resolution of this object, the smaller the D is, the further out, the larger this angle alpha is, and the further out this diffraction peak goes in the diffraction plane, in the back focal plane of the simple Fourier transform lens. Then so if D gets to be very small, this goes further out, further out, further out until it hits the aperture. And that, of course, then means that it's no longer part of the image. And we just saw a story about diffraction contrast this morning. This energy will disappear from the primary wave here, but you see that as a dark area now suddenly, because that information the energy has been absorbed by the aperture. So if you have a phase contrast object here, that information will disappear, and you essentially will see this information will not hit the image anymore. And so this cutoff caused by the aperture is what is in this Rayleigh criterion. A famous formula here with the numerical aperture of the lens, n is the refractive index of the medium, lambda is the wavelength of the light. This effect of the information disappearing when it hits the aperture, you can see in a transfer function. This is an intensity transfer function. The transfer function of that system is at a very low resolution. Everything gets through until you hit the aperture, and then everything stops. So you have a sharp cutoff of the information when this diffraction peak hits the aperture. The story is not always the cutoff in reality is not necessarily this sharp, and that has to do with the coherence of the illumination system. And especially in light, in light microscopy, you can have a large source, and that makes that the information will actually go beyond this resolution limit, but it's dropping gradually just due to the size of the illumination source. I'll get back to that for electron microscopy case. So here's the Rayleigh criterion explained. And in this case, the +1 diffraction peak and the -1 diffraction peak and the zero order beam, you can all see here in the back focal plane. So this machine, this optical system, is a Fourier transform machine. And so the signal that you have here is Fourier transformed here, and you're in the diffraction plane here of that object. But in this diffraction plane, you have the +1 diffraction peak and the -1 and the zero order peak. But the important information in this plane is coded in the phases of these diffraction peaks, and that is the very big difference between electron microscopy and X-ray crystallography. I'll get back to that later. In X-ray crystallography, you collect diffraction data, and in electron microscopy, you also often collect diffraction data. And if you image this, you get the diffraction peaks only, but you lose the phases of the diffraction peaks. And the phases of the diffraction peaks you need to build the image. Let me just switch off the projector for a second. I have here a CD that I borrowed from Kalunga yesterday. And the most interesting CD when you buy a pack of CDs that you can burn yourself is the one that's on top, that has no metal coating. You can actually not use it to record any information. But the nice thing is it has these set of lines here. All the grooves that you have in a CD are all here, and therefore I can use that for a diffraction experiment. So here's my zero order beam now for you on the screen. So here we go, zero order beam, and now I put this object in my beam. And this is a sequence of lines, as you all know. And you now see that you have a +1 diffraction peak, and you even have a +2 diffraction peak, and then it stops. So a simple diffraction experiment was the cover CD of a stack of CDs. So don't throw this one away. This is the most important. You can throw the CDs away. But this is, I bought a whole pack of CDs just to get access to this one. And I never used the CDs. I gave them away. Okay, so this diffraction experiment, and as I said, is very different to collect diffraction data from collecting image data, because in one case you lose the information of the phases, and I'll get back to that. This little device, this little Fourier Transform device, was something that we used to use daily in an electron microscopical lab. You would have a setup with a single lens and a laser pointing at this plane here, creating parallel waves hitting this plane. And in this plane, you would put the micrograph that you just took. And if you did that, then you could see here in the diffraction plane, in the Fourier transform of that of your image, you could see how good your image was. And here is such an image taken. It's a micrograph taken on a CM300 some 12 years ago. And this is a micrograph of carbon foil, and on top of the carbon foil, the tiny little gold islands. And so here you put the micrograph into this optical diffractometer, and the optical diffractometer then gave you the power spectrum of that image. And here you see the power spectrum of this image. And since there are all these tiny little gold islands, you can see, and gold diffracts very strongly at 2.3 angstroms resolution. You know that better than I, because we never look at metallurgical samples. But so only as in test objects like that. And you can see here that the microscope is giving this very high level of resolution for biological specimens. But what I wanted to emphasize here is that this little Fourier transform property of the single lens is used in a routine instrument, in what was a routine instrument until recently. Since today, you will be collecting these images typically on a CCD camera directly. You don't need to put it in an optical diffractometer. You just press a button and say Fourier transform, or amplitude spectra, or whatever the button says, and you will generate this directly in the computer. And so if your image is not good, you immediately see that the power spectrum of that image is also not good. So there's no immediate need for this Fourier transform lens anymore, at least for this apparatus that was used for decades as a quality test of the microscopical images that you generate. But the Fourier transform of that lens is the important issue. And this is one Fourier transform. If you now take that lens, doing one Fourier transform, a constant into a point, into a constant, and you take a second lens that transform this constant to a point, you have a double Fourier transform, and this double Fourier transform images a single point to a single point. So that's an imaging device. And this is the most fundamental device in Fourier optics, in microscopy, in all kinds of imaging systems, in all linear imaging systems. This even applies to radio telescopes, optical telescopes, your photographic camera, the beamer up there, or the beamer here. All these devices are imaging devices that you can describe by this simple symbolic apparatus of doing two Fourier transforms in a sequence. And the imaging system will will reduce the amount of information for, as I said earlier, because you have a limited aperture. So not everything that leaves the object will actually reach the image. And you can have the microscope can be out of focus. It can have aberrations, which you think of being placed in this, in the diffraction plane here. So anyway, this is a very fundamental step in the optical sciences. And this is the same thing now, made a bit more neatly designed. And here we see your object, this periodic object that we've seen before, with its two diffraction peaks, and then leading to an image. An image, as I said, is very different from a diffraction pattern, because here you have an interference pattern created by these diffraction spots here, but using their phases as well. And the image you can only build up from the object if you keep if you keep track of all the phases. In X-ray crystallography, you collect the data here, and you have a hard time finding the phases of the diffraction peaks so that you actually have an image, a three-dimensional image of your crystal. This understanding of the fact that a simple imaging system is a double Fourier transform came around the 1930s. And here we see Fred Zernike, who was a professor of theoretical physics at the University of Groningen in the Netherlands. And he was a theoretical physicist, but he loved to tinker with lenses. And he had a very fundamental understanding of what was happening. This type of fundamental understanding, and the understanding that the zero order beam goes through the stays up the optical axis here, and the diffracted information is away from the axis, from the optical axis in the back focal plane. So you take the object away, you keep the zero order beam. You put an object in, you have these diffraction peaks. But that means that in the back focal plane, you have a unique opportunity of manipulating the diffracted information and with respect to the not diffracted information. So he built this machine here, which is exactly the same thing as the previous slide, only he put a tiny piece of glass here. And all this piece of glass did is change the phases of the zero order beam with respect to the phases of diffracted information. And since he couldn't specifically manipulate the phases of the undiffracted beam with respect to that of the diffracted beam, he can suddenly make things that were completely transparent, live bacteria, make them dark, make them appear dark and black and white in the image. So something that was not visible because it was completely coded into the phase information suddenly became visible. It doesn't matter whether you change the phases of the undiffracted beam with respect to the diffracted beam or the other way around. Here you see the first half of that optical system again, just a simple Fourier transform lens, and the phase plate, as this piece of glass is called, now operates on the diffracted beam rather than on the undiffracted beam. It doesn't matter as long as you have a phase difference of 90 degrees or minus 90 degrees, or you introduce an extra phase difference of 90 or minus 90 degrees between the zero order beam and the diffracted beam, that allows you to make a phase object visible. Here is what a phase object does. If you have a phase object, you can think of the wave as this unit vector here. If you have a modulation of the intensity because some light is taken out, then what comes out is a bit around an average will be sometimes more and sometimes less, darker and lighter. If you have a phase object, all the light that hits the object will come through on the other side. And all that happens is that at areas where the sample is a bit thicker, it will take a little longer for the wave to reach, to pass through the object. And that means that the phase may be delayed by a little bit. So that goes in that direction. But so you have a modulation in this direction. But the amplitude is not changed. So a phase object changes only when this arrives, this wavefront arrives, but not how much light arrives. And when you take an image, you just get the length of this vector. You find just the energy. And as a consequence, you don't see anything. But if you have a phase plate and you rotate the phase 90 degrees or minus 90 degrees, then you can rotate this phase direction. You have a phase object doing nothing, But if you change its phases by 90 degrees, suddenly that becomes a modulation in this direction. And so suddenly you do see something that you shouldn't be seeing. So this is the same story again. The amplitude object will modulate the intensity, but the phase object will not modulate the intensity. It will only modulate the phases. And to make this visible, you need to rotate, change the phase by 90 degrees, and thus you have an object that is modulating in this direction, then becomes a modulation in this direction. It's just a little complex notation that one uses for this. By the way, if you have, sorry, let me go back to this one here. If you have an amplitude object, you have an intensity modulation in this direction. If you have a phase object, you have a modulation in this direction, and you don't see it when you take a picture. But if you rotate the phases by 90 degrees, then this modulation becomes a horizontal modulation. You start to see it. But if you have an amplitude modulation in the same object, that will also rotate by 90 degrees, and it will become a phase modulation. So actually, even though you're taking energy out of the system, you don't see it anymore, because the amplitude object is now suddenly coded as a phase object. So when you have maximum of transfer of the phase information, you automatically have a minimum of the amplitude information transfer, and vice versa. And so I'll have a demonstration of this later. So the person who realized that in the electron microscope we have a phase contrast mechanism is the most important source of image information is this guy here, Otto Schatzer. And I took this picture of him at one of my first international conferences some 40 years ago, 30 years, whatever it was, a long time ago. And I was a PhD student at the time, like you are now. And so I had a chance to chat with him. They invited the PhD students to meet the famous professors. And I chatted with him at the barbecue. And he was already here. He was in his late 70s, and he was still working at the university. And I asked him why he had not retired yet. He said, well, it's just a matter of money. He works for 3, and if the university let him retire, they would have to hire 3 professors in his place. So it was not an economic viable. That was his. Anyway, a very friendly man. What he realized is, this is a very old drawing, as you can see, that in the electron microscope, you have a faceplate that is almost ideal. And although it's not actually built in at all, it's built in because this faceplate is built in just because of the aberrations of the instrument that are difficult to correct, and not by anything else. If this is already known from light microscopy, if you defocus an object, if you have like a transparent object like bacteria swimming in water, and you take an in-focus picture, then you don't see anything. The bacteria completely disappear. But if you defocus the microscope by just going under or over focus, you get instead of a plane back, so a point being transformed into a plane in the back focal plane. If you have a point that is not in the front focal plane but a little bit over or under, then what comes out here is not a plane wave, but is a spherical wave. And this spherical wave, there's a difference between its position and the ideal plane position, and either in under focus or in over focus. So here you see that picture again. You have an effect here. This is just drawn this a bit bigger. So you have here that spherical wave is not in the ideal back focal plane, the flat, and it has an effective difference. That wave has an effective difference to the ideal plane, which can be a quarter of a wavelength, half a wavelength, 3/4 of a wavelength, etc. But this is effectively just a faceplate, just as good as a physical faceplate, even better because it's not affected by all kinds of other problems as you may have with a real faceplate. Here, you have no transfer of information or phase information. Per definition, at the origin, you never have transfer of phase information. The phase information is always relative to the background, and if the background is relative to itself, it's undefined, the phase. So you never know the phase at zero frequencies. That's here at the origin. But if you go to higher resolution, then a higher resolution is further away from the optical axis in the back focal plane. Then here you suddenly have a quarter of a wavelength difference between this flat plane, the back focal plane, and where the waves emerging from your object actually are. And this difference of quarter wavelengths is exactly what a faceplate would do under ideal positive phase contrast conditions. So here you actually have perfect phase contrast. But if you rotate the phases by another 90 degrees up here, then you have 180 degrees difference. And again, your modulations that were in the vertical direction have rotated, but they're vertical again, and you don't see it. And then if you go further, you have 3/4 of the wavelengths, that is a 270 degrees phase change, and here you have perfect negative phase contrast. So you do have, if you defocus a conventional light microscope that is not a phase contrast microscope, you can still see bacteria, at least in the high frequency regime, fine detail regime. You see, for example, black edges appearing around the bacterium. So this was known in light microscopy, and if you see the first papers by Zernike in 1942, he talks about these things, the first papers on phase contrast. And what Scherzer realized is that the effect of underfocus that I've just explained to you, the electron microscope has another built-in property, and that is the spherical aberration. It's an aberration, it's an error, an optical error, so to say. And by the combination of these two, it's very difficult to compensate for this spherical aberration, and it's very often the question whether you even want to compensate it. If you want to go to extreme resolution, you may have to use a spherical aberration corrector. But for biology and under normal circumstances, this combination gives you the sum of these two phase errors, gives you aberration function in the back focal plane that behaves almost like an ideal faceplate, with a phase shift of 90 degrees lambda over 4 over a wide range of frequencies. So if you have a 300 kilovolt electron microscope, then you have a band here, and this is probably the first series about 3 angstrom resolution. And this is in biology, you would be very happy to have a map at 3 angstroms resolution. So the combination of a certain amount of underfocus and spherical aberration gives you an effective faceplate that is very, very strong. And this that is very good to very high resolution, depending on your field of science, I must say. What high resolution is depends on the perspective. But so this focus is called the Scherzer focus in honor of Otto Scherzer, who thought of this combination. And so this was all hand drawn, and in reality, then you have, of course, nice functions that describe this. And here you see the situation very close to Scherzer focus, where you have a fantastic resolution. This is 2 angstrom resolution. This is about whatever close to 3, beyond 3 angstrom resolution here, where you have a very good transfer of information. Now, it depends on your field of science whether this is very useful for you or not. And material science, you may very often want to focus at Scherzer focus, because there's a very simple interpretation of the data up to this 3 angstrom limit. In biology, biological macromolecules that we like to look at, there is a problem. You have brilliant high resolution, but very poor transfer of the low resolution information. So if this is 2 angstroms, this would be 4 angstroms, 8 angstroms, 16 angstroms, 32 angstroms. Particles of a typical biological molecule is 100 angstroms in size, and the big contrast just from the big particle being there is all in this regime here. And there's so little contrast in the 50 angstroms that you don't see the particles. You completely lose the particles that you want, that you're interested in. So what you often will do in biology is to go much further out of focus. So this is about half a micron, which is still very close to, considered very, very close to focus for biological samples. But if you do this, then you see that this first maximum of the transfer function moves to much lower resolution. and because it suddenly you do have a substantial contrast in the low resolution regime. So the phase contrast of these phase objects suddenly become visible that are not visible. So you have fantastic resolution, but you lose your particles here. And here you have a good resolution, you have a good contrast, but the transfer function starts oscillating wildly at higher resolution. And that is actually, this picture is not very realistic, because if this starts oscillating, then what you typically have is that you have information will be damped out by all kinds of reasons. And one of the important reasons is the partial coherence of the electron beam. Even if you have a field emission gun, that partial coherence will tend to drop the information to very low levels, and that's much more sensitive out of focus and far out of focus than close to focus. This is a lot of theory, but the question is, if you have a transfer function like this or like this, what does that actually do to your image? Your image, this consists of low frequency details here, a little bit higher, higher. But when you have a contrast reversal of this nature, it actually means that black becomes white and white becomes black. This is one of the most important parameters. You need to make sure that all the data that you're collecting has the same phase. If the phases are flipped over, the information will average out. So knowledge of the CTF is very fundamental, and that is throughout all sciences that use the electron microscope as an imaging instrument. And the way we tend to test optical systems is to look at objects like this that have a whole range of spacings. This is called the Siemens star, and it has a whole range of spacings in one single image. And you can see what the optical system is doing to your object directly. So in terms of our biological specimens, we would be interested in, say, 30 angstrom resolution out here, and you go in here, you have 3 angstrom resolution at the inner part of this Siemens star. And the question then is, what does the electron microscope do to my images? And this is just one that doesn't have the text on it, and the reason is that I just want to now switch projectors for a second. I'm going back to that in a while, but okay, very good. So you have the 30 angstrom information out here, and you have the 3 angstrom information down here. Now, if you defocus the electron microscope, you have the same effect as you will see here on. I'm now defocusing the projector here, and I think the defocus is the top one. And you see, for example, here, again, press the right button. Here you see that what was white here becomes black. There's a contrast reversal that is moving through the image here. And let me see if there's it depends very much on the projector. This one here, this direction is maybe better. As you see it very clearly here, you have a dark band and it becomes a white band, and vice versa. See, there's the contrast reversals up here and up here. You have 2 contrast reversals. You see a band here of contrast reversal, and depending on the focus, so you can change what was white, what was dark into light, and light into dark, just by changing the focus. And so this is now you can see it very clearly here. For example, out here is a contrast reversal band, and above that the contrast is different than below. If I'm now lucky, we'll switch back to the other projector. So this is an amplitude object. This is absorbing light, and even though it's absorbing, now I'm not talking about the light, the electron microscope, but I'm talking about this projector here. So it is still capable of flipping the phases of the information and perverting or just changing the what is black into white and vice versa. So here this is the same picture I used before on the other slide projector, and this is the calculated effect. Very often I cannot reach the projector on the ceiling like here, and I just have to show you what the contrast reversals are depending on the defocus. So you see here, just under perfect circumstances in a model calculation, how you get a completely flip over of the contrast all the time. In single molecule, when you're doing electron microscopy of biological specimens, the radiation sensitivity of the samples is such that you cannot sit there and focus the image. You have to take a picture and use it as it comes. And from one picture to the other of the same sample, you may have a complete reversal of the contrast. You need to understand that and manipulate that information. Otherwise, you will be averaging images with positive and negative contrast. And when you average images that have positive and negative contrast, you lose everything. Now, a little bit again to this fundamental difference between intensities and that you collect in X-ray crystallography or in diffraction electron microscopy and images. So when you collect data in the diffraction plane, you have the intensities of the diffraction spots, but you lose the phases of these spots. And the phases of these spots you need to create the image. So in electron microscopy, you collect this, you collect the intensities here, and these intensities have the phase information in the diffraction plane already built in. So you're actually looking at the object and not at the diffraction pattern of the object. Two very different things. So a classical word in electron microscopy and in X-ray crystallography is the phase problem. But the phase problem is not of X-ray crystallography is not the same as the phase problem in electron microscopy, because the phase problem in X-ray crystallography is you have the diffraction spots, and you want to know their phases so you can create an image. In electron microscopy, you collect the images here, and these images already contain the phase information in the diffraction plane. You do lose phase information here, but this is phase information that you're not interested in because you may, depending on the kind of object. This phase information here, if you have a perfect phase contrast microscope, is the amplitude information in the original object, and that is typically very weak. And you're not in biological objects. You're certainly not interested. So there are two different. You lose phases here, but these are not phases you're interested in, and you lose phases here, and these are the essential phases. So the phases you lose in electron microscopy and in X-ray crystallography are two very different phases. Now the question is, why do you lose this information? So same story again. X-ray, you lose the diffraction intensity. You collect the diffraction intensities. You lose the relative phases between the diffraction spots. And in electron microscopy, you don't have that problem. The relative phases in the image are lost in the recording, but these are not important for weak phase objects. So the question is, why do we lose the phases? Just fundamentally, what is the fundamental principle? Why, when we record an image of electrons, we lose the phases? Here, there is no fundamental necessity to lose phases. Or here we see two human beings jumping over a wave, and this may be in Guarujá, I don't know, Santos. But these kids are able to jump over the wave. They are sensitive to the amplitude of the wave. If there's a very big tsunami wave coming at you, you realize that something is wrong and you run away. So you are sensitive to the amplitude of the wave. And since you can jump over a wave, you can synchronize your actions with the phase of the wave. So here, for ocean waves, we can see the phases and the amplitude. So we're perfect transducers of the waves. This is another perfect transducer of the wave. In this case, radio astronomy. And radio telescopes, they operate with wavelengths of 20 centimeters or thereabout. That light takes some time to travel 20 centimeters, and that's enough for all our electronics to actually measure the phases. And we can synchronize the information coming from all kinds of dishes separately. And So we can do as if all these telescopes were just one big telescope looking at the same thing. And you can synchronize all the radio telescopes around as if they were one big, huge telescope, just because we can collect the phase information here too. And sometimes experiments are done such that the Earth is traveling around the sun, and you're looking at the same area and you synchronize that. So you can make a huge synthetic aperture, a very high resolution in terms of Rayleigh Criterion, and you can that way decode information that's coming from the sky. So no fundamental problem in recording phases. The only problem that we have in light and electron microscopy is that of our transducers not being good enough. So if you take a photographic film or a CCD camera, I need to adapt my slide, using a very short exposure, thousandths of a second, during that time, light waves have traveled 300,000 meters. So that's the equivalence of, there's a one missing here, of 10 to the 10 wavelengths. There's so many wavelengths passing through your film, you can simply not follow these fluctuations. Our transducers are too slow to measure X-rays or photons. It's just we're not good enough at measuring these things. And so this is why you lose the phase information. There's nothing fundamental about it. There is some fundamental problems actually when you would want to record the phases coming from an X-ray crystal, for example, because a crystal in X-ray crystallography is something macroscopical. It can be a millimeter thick or half a millimeter, and so everything that if you would be able to do the phases of a crystal, then everything would have to be flat within a half an angstrom or thereabouts, because that's the wavelengths that people use in X-ray crystallography. And doing something that is precise to half an angstrom is impossible, because the distance between one atom and the next in any material is a couple of angstroms. So take one atom away, and you're out of focus or out of sync with the rest of the lens. But there are lenses for X-ray crystallography, but these are all very, very small angles that can be used. No phase information. And in X-ray photons or electrons, the situation is even worse. So we lose the phases just because our transducers are not fast enough. A few more tiny issues, really, until I come to a close. And one of the issues is astigmatism. Astigmatism has the name of being something very bad, and it can be something very bad. It's not necessarily true. I'm now using very astigmatic images to show you some principles. Here, I showed you this double Fourier transform system. So here is the Fourier transform of the object, and this is then Fourier transformed again. I had a single dot here for the 0 or the B, and now I put an extended source in of size S. So here is the condenser system is now part of the optical system, and instead of this, so you have an image of the source here, and you have an image of the source in the back focal plane, and things change a tiny bit because it's no longer a single dot, but it's an extended source. And all sources are extended sources in electron microscopy, even a field emission gun. And the only reason I put this here is just give you the effect of the of the source size to the transfer function. I've shown you transfer functions that were linear. I've showed you transfer functions that were linear curves, and now in the back focal plane you saw a Schatzer focus. Let me draw that one. It was just the maximum and start oscillating out here. So, but in essence, what you have in the back focal plane is a plane. It's not a single transfer curve. It's a two-dimensional plane. And when you change the optical system to become astigmatic, then your transfer functions become two-dimensional. So this is what you're looking at. These are transfer functions, two-dimensional transfer functions. And these transfer functions are for a 300 kilovolt Cryos instrument that we have been using a couple of weeks ago. But what I wanted to show you here is you see this in this direction, you're pretty far out of focus, about 17,000 angstrom out of focus in this direction, and 1,500 angstrom under focus in this direction. Now, because the image is astigmatic, you have different properties in two directions. What I wanted to show you is actually this area here. You see that things are oscillating very rapidly. Whenever you have an extended source, you will average out. It's a convolution with the size of the source here, and the information tends to then average out in that direction. So the partial coherence of the system tends to affect the high resolution information more than the low resolution. And the reason I put astigmatism is that it doesn't have anything to do with high resolution, because here you have very high resolution in this direction. So if you have an ideal small source, then the information will go out to a higher level typically than if you don't have a full level of coherence. In the new Cryos instrument, you have a very good control, or in the Titan, you have a very good control over you have 3 condensers rather than or 4 condensers rather than just 2. And that allows you to play with this much more than was ever possible in the past. So if you have a fully coherent system, you see that even when you are oscillating quite wildly, far out of focus, you can still have that information. You need to correct it in order to interpret your image. But if you have partial coherence, it will then actually disappear from the data because of the integration over the source. And that is not just a matter of resolution, because if you are far out of focus, then yes, then it will suppress that information. If you're close to focus like here, it has a very small influence. So and this is for biological specimens where you need to go far out of focus in one direction to have enough contrast, is an important issue, because you lose the high resolution information. If you want to have 3 angstroms information, then the partial coherence is maybe limiting your system. Partial coherence suppresses the high resolution information. It actually doesn't suppress the high resolution information. It suppresses those areas of your CTF that are oscillating rapidly. And that normally are high resolution areas, but it need not be if you're close to focus. Here, same picture again, just some of the parameters. The highest resolution is 0.8 angstroms or 0.9 angstroms here. And spherical aberration, these values come from a Titan. 1700 angstroms resolution, defocus in this direction, 15,000 here are the real values. And the calibrated focal distance of the objective lens, 300 kilovolts. And here is the millirad, so 0.18 millirad beam convergence. Now, why we are interested, this is my private, this is not just our private little research thing now, this has nothing to do with your course. Now I want to talk a little bit about my thing here that we've been playing around with. This is why we are looking at astigmatism. We want to do astigmatism for just this reason, that to see your particles, you need low resolution contrast. And that means you need to have a strong defocus to see your particles. But if you see the particles, then you lose your high resolution information. So this is where we start. Well, let's compromise. Let's do close the focus in one direction and large defocus in the other direction. And since we have many particles, the particles will be randomly oriented in this direction, in the plane. And so you can still recover all the information you want to have. And so this is why we've been playing around with the idea of doing astigmatic images. And in the old days, people would say, if you have astigmatic image, throw it away. And now we're starting to rethink, hey, very strong astigmatic images may actually have more information than a image with a perfectly corrected astigmatism. And so this is where we started to play. And here, look at this, the Siemens star that I tried to make you familiar with now. And then this is in real space, and this is the CTF that we're imposing on this image. And so this is what the image suddenly looks like. It looks a bit weird. You see all these contrast reversals. It looks very much like the image of the Siemens star that you've seen from the beamer here, from the CTF, from the projector. But then you can correct for it. So you have all these contrast reversals. But knowing the transfer function, even if it's a funny one, it allows you to correct it. And so at least they're still a bit jiggly, but it doesn't come with the wrong phases like here. It doesn't come with the wrong, like you would have here. And so you would have some images in this direction, and since the particles are rotated in all kinds of directions, you do get a complete coverage of the information, and you can retrieve all the necessary information. This is just the influence of the voltage. I was just playing around with it the other day, and here's 300 kilovolts, and you have only 100 kilovolts, then the information drops much quicker. These were my thoughts on CTS.